Good morning, everybody. How are you?
Good morning.
Glad that it's not so cold outside. We've had a very mild winter so far. It's not been, we've not lacked for thermal energy. How's that? Yes?
I noticed that we had like a bunch of hot winters in a row. Do you think that that could be a thing from, I'm not saying necessarily global warming, why do you think that there's been a series of hot winters? Like, it's been happening for the past
Well, the first
5
question
years.
I would have is it really? Because our perception as human beings is very skewed.
Yeah.
And so, it's really interesting. I've taught other classes in the past. One of them is quality control. Quality control was one of the classes that I highly recommend you guys to sit through and try not to fall asleep through. Because it's one of the most valuable classes you'll ever come across. Unfortunately, I never could figure out how to teach it where it wasn't super boring. So I threw in a whole lot of Dilbert jokes and things, but the idea behind quality control, there are a couple of ideas. One of the things that's really, and see, I never took quality control in high school, or in college, and I never did a whole lot of it in industry, and then, they tossed the course my way and said, here, teach this. So I went through the book, of course, and read it and tried to apply it to my life the best I could. I ended up applying several of the ideas. One of the things that was, there were two big things that stuck out to me, and they're obvious things. One of them was really interesting was, you can't control something if you don't measure it. Until you have measures of things, and I would say there's a corollary to that or something related. I don't know if the corollary is the right word, and that is, you don't really know anything about something until you measure it. And so, that may very well be the case. I'd like to see the measurements and see the data over time, There's been a lot of things that I've tracked over time, and it's been really interesting to watch. And that's one of the things that the quality control course had, was statistical tools that showed you how to actually monitor some variable over time and be able to say something about it statistically. Another big thing that stuck with me was that data without, and it was, I've forgotten which person it was, because this borders on philosophy, right? This whole thing about quality control, because what is quality? It's a philosophical question. Well, anyway, one of the other things was that data without variation is false data. What that means is, if I tell you that my car gets 45 miles per gallon, that doesn't tell you much, right? Because you'd like to know the range. Is it 45 miles per gallon? Okay, that might be the average, but maybe some days I get 70 and other days I get 10. That's a very different quality than 45 miles an hour, sometimes 46, sometimes 44. You see what I'm saying? And so just saying the average doesn't tell you anything. The variation in the data is also important. And that's one thing that really stuck with me. And I hope one thing that all of this does for you, that this whole degree you're working on, I hope it does something for you that it did for me. I hope it humbles you. And what I mean by that is not that any of you are arrogant. I just hope it helps you realize how little as an individual you actually know, and how much you need the people around you. And I don't mean that I was ever an arrogant, I need no one type of person. I like people, always have. I've not been a real extrovert, and I've kind of learned to speak to people by doing this job. And I'm glad I've had the chance to review all these. But I see a lot of people, and people in my own family, that they're very intelligent people, but they never went to college, and they never went through that. I don't know how to describe it. To me, it's kind of like a trial by fire, where you go through this, and you get shown over and over in subsequent classes that you really don't know much. And it's a good thing for you. It really is. Because I went to college, I did think, I'm gonna do really good here. I'm gonna, discover some interesting things and, get patents or whatever, because I wanted to be an inventor. And then I get to the point where I'm actually a design engineer finally after graduating college, and I realize, boy, I'm hardly qualified for this job. And it's a good perspective. It's not that I wasn't qualified for the job, it was that I realized that although I had learned a tremendous amount, there was still a tremendous amount more to know. And I hope you get to that point, because all we can really do here in the 4 years we have is build a low foundation. That's all we can do. But I appreciate your question, but I have to give you some of my philosophy as an answer, So there's all kinds of problems in the world, and that's good and bad news. The bad news is that we have the problems. The good news is you guys are all problem solvers. That's what engineers are. In fact, I don't know if I told you guys, I visited a couple of our students what was it, 6 months ago or so? They work at Ice and Drivetrain now. One of them had worked for GE and Cummins and I don't remember where else, and the other one had worked Samtec and just all kinds of different, relatively local companies, 4 or 5 different places each, I think. Not that they've been fired. They had the opportunity to move on and advance their career, so they did. And they, I was talking to them about, because they were giving us this donation of tooling and things that the company didn't need, and we really appreciated it. But they'd been out of the program for 6, 7 years. I had seen both of them start and finish their degrees. And so I asked them, I said, now that you've been out there, now that you've had the chance to apply what you learned, what should we change? What were we doing that wasn't good enough? And they said, well, there's 2 things. Number one, you need a project that runs longer than a semester, something where the students are responsible for something big, where they can get the chance for things to kind of fall out, the floor to fall out from underneath them, where things just don't go right, and they can experience that and realize, okay, I still have the responsibility to get this done even when things don't go right. How can I plan ahead? How can I have backup plans? How do I change on the fly? How do I make things work anyway? And so I said, oh, guess what? We have something the students hate called senior capstone, but that's exactly what we are putting the students through on purpose, because we know they need that. And so they were actually glad to hear it. They were also glad to hear that they didn't have to go through it. So I'm sorry if you don't like it, but there is a good reason for capstone, even though it may seem like a mess at times. The other thing they said, oh, I've lost my train of thought. I had something good there. It'll come to me a little later. Anyway, it was just interesting because they really, I know what troubleshooting. They said, it doesn't matter if you're at GE and it's dishwashers going out the door, or, it's making you money, or if you're at Cummins and it's engines going out the door, or you're at Ice and Drivetrains, it's transmissions going out the door that's making money for the company. It doesn't matter what it is. Your job as an engineer is troubleshooting. It doesn't matter if it's troubleshooting on the line that's making it. It doesn't matter if it's troubleshooting on the part that's not being made right. Because ultimately, even when you design something new, there's going to be problems. You have to solve those problems to make it work right. So the bad news is there's still trouble in the world, right? The good news is you're all trouble solvers. And I hope that you will all realize there's plenty of work to be done. Those of you, how many of you have been out in industry practicing as an engineer? There's a few of you. Is what I'm saying true? Are there still problems to solve? Are you amazed that companies can survive as they are, as inefficient as they actually are? There's all kinds of opportunity for making things better and making things more efficient as far as the relationship to this class goes. There's plenty of opportunity, plenty of things to do, and quite frankly, I'm glad you guys are here. I'm glad that we're training people to solve these problems. Yeah.
I feel like the problem that maybe some engineers in the field can't overcome, though, is like the culture of the company.
That's a big problem.
The way, you can change the machine, you can fix materialistic objects and solve problems that way, but
True.
if it comes to changing the culture of the place that's actually there,
you are limited somewhat
yeah.
in how much you can change the culture. The nice thing is we're all free and we can change our jobs. And so if you end up in a company that doesn't treat you well or that you feel is not doing something ethically, it's good to move on. That's not a bad thing. In fact, there's a recommendation I've heard that you don't stay in a job more than 4 or 5 years. There's a couple of reasons for that. One is that your career becomes somewhat stagnant. You kind of get pigeonholed into that area, which you may or may not want. The other reason is that as a professional, you should always be looking for the next opportunity, and in that amount of time, you will likely find something better than what you're working at. The other thing is that this is actually the quickest way to increase your salary if you're interested in that. The quickest way to move up is to actually change positions and go to a different company or a different job within the company if it's big enough. On the other hand, you don't want a job hop, 6 months or so. You want to stay longer than that. But anyway, anything else you guys want to mention, talk about? I like that we bring up these discussions every now and then because there's more to engineering than the hardcore physical principles.
Can I throw up one thing that I've
Please
run
do.
into that
Yeah.
I'm kind of surprised that we weren't pushed
Sure.
more early on?
Yeah.
Was I ran into needing to throw together a what was it? Profile resume? No, portfolio resume.
Okay.
And that kind of caught me off guard, so I have to dig back through everything.
Yeah. Yeah, there was one student that came through our program. I'll never forget him. His name was Michael Fuchs, and he good decent student. He was, you know, a good guy, real nice guy. He was, when he came to us, he was working at Advanced Auto Parts, I think in New Albany. And I sat down with him and we wrote a resume, and he got an internship. Where did he get an internship? I don't remember right now. Oh, Key Electronics, that's where it was. And he went to Key Electronics, and he did something very clever I've never forgotten. He did some clever things for them. He ended up saving them about $100,000 a year or so with some of the projects he worked on. But what he did clever for himself is he kept a binder of all the projects he worked on during an internship. And then he came back to me after that, and we wrote a resume that was a killer resume because he had details about all the stuff he'd worked on. He didn't forget anything. It was all right there in the binder. In fact, we met probably 4 or 5 times, spent about an hour or more each time, writing just all these different bullet points of stuff he had done and skills he had honed. And he, like I said, he had a wonderful resume. Honda picked him up immediately, and then he's moved a couple different places since then, I think. He's just, you know, his career took off because he did something clever. He kept track of all the stuff he had worked on in his internship. So yeah, a portfolio basically, it's helpful because it gives more insight to the company about what you've done and what you can do therefore for them. So this is a good discussion. I like this. It's not exactly thermo. You guys trying to keep me away from thermo? Is that what's going on? I got it now. This is a plan. We're going to talk about everything to distract us. Anything else before we move on? All right. Last time we talked about the lever arm rule and this idea that all of the properties of a fluid are related to one another because you really only have 1 degree of freedom. Get the sense that PowerPoint's about to crash with all these animations. Nope, there we go. So far, so good. So I hope you wrote down these 2 equations, although they are not independent. They are the same equation, just rearranged. All right, there is, however, a simple relationship between properties that you already know. It's this one, PV equals MRT. You may have learned it as PV equals nRT, and of course in this class we use it as PVRT, or equals RT, where V is the specific volume. Okay? Now this is an equation that relates properties. It relates pressure, temperature, and volume. Now you realize how many degrees of freedom are there in this equation? In other words, how many variables could there be before everything is set? Well, R is not a variable. If I were to specify temperature and volume, then the pressure is something you can compute, right? So this has 2 independent degrees of freedom, or 2 degrees of freedom. So if I had an ideal gas, that means I could specify 2 independent intensive properties that don't depend on how big the system is, and calculate all the others. As a matter of fact, once you knew the temperature and, say, pressure of an ideal gas, its other properties like the amount of thermal energy it has and so on, all those things are set because there's only 2 independent variables. It's interesting that the properties of fluids are so closely related to one another. Okay? So we can use this information, for example, to find out how much mass of air is in the room. And we've done that in the past, and I think you guys were surprised in 220 how much mass of air there is in a typical room. Now this doesn't work for water. That's why it's called the ideal gas law, right? This is not the transcendent equation that relates everything together, right? It's not that. This simply relates properties for an ideal gas only. For other things that are not ideal, we need other equations. In fact, you know what? Let's do something interesting right now. At least I think it's interesting. Does steam behave as an ideal gas? Couldn't we figure it out? Let's go to the property tables. I don't care if we, I guess let's go to metric. Why not? Metric property tables. Why don't we go to the superheated water tables? Because in the superheated region, certainly the steam is not close to condensing, right? As long as we move up to a relatively high temperature. And I don't really care which region we grab. I'll just try to make the math easy. We don't have enough room on the board, or I'd write this down. So if you're watching the video, just follow along. I'm on page 919. I want to grab your calculator and work on this with us. Let's just take 1 megapascal. Why not? A megapascal, that's what? About how many times atmospheric pressure is that? About 10. Because atmospheric pressure is about 100 kilopascals. So a megapascal No. Yeah, 100 kilopascals. That's 0.1 megapascals. So this is about 10 atmospheres. If we're at, let's say, 1,000 degrees Celsius, well, do I want that one? Yeah, why not? 1,000 degrees Celsius. You can read off the specific volume. Do you see it there? 0.58721. What three variables did I just express to you? Pressure, temperature, and specific volume, right? Are these related by the ideal gas law? How could we figure it out? Well, we'll need the gas constant in order to plug it in, right? We'll need R. So keep your finger in page 919 or put something there. And let's go find the gas constant. That would be on page 908. On page 908, do you see a gas constant for steam? Some of you are looking at the page and saying, I see one for water.
There's one for steam on 909.4615.
Well, if we look on 908, do you see where water is listed?
Yeah.
You see that's the same gas constant?
Yeah.
So when they say water, what do they mean? Do they mean liquid? No, they mean the chemical H2O, you see. So just like me, when I talk in this class, when I say water, don't think necessarily liquid. I just simply mean the chemical water. So the gas constant you found is correct. It's 0.4615, and the units are kilojoules per kilogram per Kelvin. So why don't we do this? Why don't we, let's see, let's calculate the specific volume. So grab your calculator, plug in the gas constant, whatever the number was, 0.4 something, 0.4615. It'll be R. We'll multiply by the temperature. Now the temperature is 1,000 degrees, so do we plug in 1,000? No, we have to plug in 1,273 because we need Kelvin. So multiply the gas constant R by 1,273 and then divide by the pressure. Now you won't want to divide by 1 megapascal because the units won't work out. Divide by 1,000 kilopascals and then the units will work. If you're curious about the units, this is working because a kilojoule is the same thing as a kilopascal times a cubic meter. And not worried about the units too much right now. So RT over P, what do you get for the specific volume?
0.587.
Now let's look and see what they gave us. You see where it's 0.58721? Pretty doggone good agreement, isn't it? That means the steam is behaving fairly ideally at these conditions. All right? Could we find a point where the steam is behaving non-ideally? Do you remember where that would be from 220? We'll see here in just a minute. So sometimes this works really well. But do you think there might be an area in this table where the ideal gas law would not work well, and it's a good thing we have the table instead to relate the properties to one another? There is. Turns out that if you're looking at steam, you can calculate the percent error. We just calculated what the ideal gas law presented or predicted for the specific volume. You can look up the actual value and take the percent error, right? Take the actual minus computed over actual. And that would give you a percent error. If you do that for a lot of different points out here in the superheated region, what you'll find is that the steam does behave fairly ideally in this region, but as you get closer and closer to the critical point, it misbehaves. It doesn't follow the ideal gas law. So if we look at a point near the critical point, well, let's get something that's a fairly high temperature, looks like about 300 degrees Celsius, and let's see, a pressure of about 10 megapascals. Let's see what we find there. So let's go to 10 megapascals in the superheated tables. And that is page 920. So now we've got 10 megapascals, and I said about 300 degrees or so. Let's see what we got. Here's 325, that should be fine. So why don't you do the same thing that you just did? Do it again. Use the gas constant. RT over P would give you V, right? Let's see how far off it is, because you should get 0.019877 if the ideal gas law is performing well. If it's not, you're going to get a different number. And don't forget that the temperature has to be 375 plus 273. Okay? So what do you get for the specific volume?
Wouldn't that be 10,000 kilopascals?
That's right, 10,000 kilopascals. You got it.
0.0228
0.0228.
or 0.028.
0.028. And the actual value was 0.01, well, 0.02 or so. It's not terrible, but it's farther off than before, right? It's wrong in the second decimal place at least now. So we could continue with this and calculate the percent error. As you get closer and closer to the critical point, you get higher and higher error. Well, that's problematic. We'd like to be able to use the ideal gas law because it's so convenient. The problem is when we get close to the critical point, it breaks down. Now, here's the compressibility factor that confused all of you guys last semester, or most of you. Okay, that's all right. We'll go through it again. Z is called the compressibility factor, and it is defined as pressure times specific volume over gas constant over temperature, and these are all real values. Okay? In fact, I'm going to try something a little different this semester. I've never tried it before. Brand new. We'll see if it works. We're going to calculate Z for a gas near the critical point. Okay? Let's calculate what Z would be, because what I'm trying to do, a lot of students think, well, let's see, PV equals RT, so say I'm not given pressure, I can calculate it. Say you're given temperature and volume, okay? And from that, from the ideal gas law, you then calculate pressure. And then what students want to do is take that number they've got, the pressure they've calculated, and plug it back in here and recalculate Z. You know what number you get every time? 1. Because all you did was rearrange the same equation. This equation is the actual values, actual pressure, actual volume, actual temperature, not ideal values. Now say I give you temperature and specific volume. Well, those are actual values. In the ideal gas law, you can calculate the ideal pressure because PV equals RT. But for the compressibility factor, you need the actual pressure, you see? Now, let's do that for just a minute and we'll see if this helps. We need to calculate the compressibility factor, let's say, for water near its critical point. So I guess it'd be a good idea to know where water's critical point is, don't you think? So let's go back to page 908 and let's look at the critical point properties of water. Where is water's critical temperature and critical pressure?
647.1 and 22.06.
Good, so 647.1 Kelvin. Subtract 273 from that if you would please. What do we get for the temperature in Celsius? The superheated table's in Celsius. 374. Okay, so we're looking for a temperature close to 374 degrees in the superheated table. And at 22 or so megapascals. So let's see what we've got that's close to 22. Do you guys feel like interpolating? Me either. So let's go to 20 megapascals. That's on page 921. And what was the temperature? 370 some odd. So again, I don't want to interpolate. Let's go with 400 degrees Celsius. Okay. Now what we're going to do is calculate the compressibility factor, or what it should be, by taking PV over RT. What pressure are we going to plug in? 20,000 kilopascals. Right? What volume? Well, the volume here in the book. And then of course you've still got the gas constant for the denominator, and you'll also divide by a temperature of 400 plus 273, so 673. Let's see how close to 1 you come. What number?
407.
0.6407. That's not 1, is it? So the compressibility factor is pretty far off because we plugged in real values. Okay, so was PV equal to RT in that case? Not even close, right? It didn't work. Why didn't the ideal gas law work? I thought it was a law. Yeah.
Good question. 921 for 17.5 megapascals is 20. Why is there 2 blank spaces for 350 degrees? Is that because it's so close?
Good question. Well, what you're pointing out is that on this page, for the sake of the camera, the question was on this page, 921, there's a couple of blanks here in these tables. And the question was, why are they there? The reason is probably easiest to illustrate by going back here. The first line, or the first row, is always the saturated properties, so on this line. and then the next data is past that line, okay? So when you look at this, if you're going down in the table, the first line is saturation. Do you see how the first upper left section needs a 350 degree temperature? See that? If you continue on over, the 350 degree temperature would end up being inside of the vapor dome because the pressure is high. Look at the saturation temperature, for example, in the middle upper section. It's 354.67. So we got to get to a temperature above 354 to be in the superheated region.
Okay.
You see? Does that make sense?
Yes.
So it's just a byproduct of keeping all the temperatures on the same line, is all it really is. Good question. So we just found that the compressibility factor would end up being about 0.6 or so. Now, it turns out that we can correlate some things together and end up calculating the compressibility factor without needing to know the actual pressure or the actual properties. We need two actual properties, but then we can get the other one, a reasonable estimate for a very accurate version of that, another way. Two questions. Go ahead.
What I was gonna ask was, when I calculated it all out, I got 1.078. Are you supposed to take that subtracted from 1?
No, you don't take a subtraction from 1. How many people got 1.07 something rather than 0.6?
Because you take, we said 20,000 times 0.009950
Yes.
divided by 0.4615
Right.
times 400 degrees Celsius.
Not 400, you have to add 273.
Oh,
So 673. Yeah.
What is the compressibility factor of 0.641 mean?
What does it mean? It means that the gas is not behaving ideally. If it was an ideal gas, Z would be equal to
why
1.
would that
I
be
guess like,
ideal?
does it mean like it can't be compressed
Instead
or
of-
like it's already compressed?
Instead of
and it's
400
compressed
degrees
further?
Celsius.
Okay, so what you're saying is why is it called the compressibility factor? I don't know why it's named that. There are two big assumptions built into the ideal gas law. One of the assumptions is that the volume of the molecules that are the gas don't take up any space. That's not exactly true. The other assumption is that those molecules don't interact with each other. They're completely independent. They never bounce off of each other. They never pull on each other. And so their behavior is ideal because of these two properties. This factor is taking into account the deviation because in reality those two things are not true. Why is it called compressibility? I don't know. I don't know why you would. There's probably a reasonable
What would you use
explanation.
it to solve for, like if it was-
So how would we actually use it to solve something? We'll get to that. That's a good question. So for an ideal gas, Z is equal to 1, right? Because PV equals RT. But real gases can have compressibility factors greater than 1 or less than 1, just depending on how unideal they're behaving and the nature of their behavior. So real gases become more ideal and act more like ideal gases at low pressures and at high temperatures. Okay? Now, here's the huge thing. I may have told you guys this, but if you had been the person coming up with this chart, you could have easily gotten probably 2 or 3 PhDs out of this. That's how important this is. This is a huge thing, okay? This chart shows you some behavior of a wide variety of gases, and these are very different gases. Methane is an organic chemical. It's carbon with 4 hydrogens. Okay, that's what it is. Water is a polar molecule. Methane is nonpolar. And carbon dioxide is a different type of molecule. Nitrogen is something that behaves fairly ideally, right? It doesn't really interact with other things. It doesn't react in chemical reactions very often, right? I mean, you can put nitrogen into your engine and run it through a very hot cycle, right? And it doesn't really react much. Okay. These are very, very different chemicals, and most of the time, chemicals that have such different natures have little in common. They don't operate the same way. And yet, look at this data. If you guys gave me data like that in one of the labs, in one of my classes, I would be so happy, right? This is beautiful data. Look how well all the data points follow the lines. Yeah, there's a few off, but this is amazing. Now, what is it? Well, it's simply a chart that plots the compressibility factor against the reduced pressure and reduced temperature. What are the reduced temperature and pressure? Well, those are just numbers that you calculate, given the actual pressure and temperature of the gas. Divide the pressure by the critical pressure, divide the temperature by the critical temperature, and you get the so-called reduced pressure and reduced temperature. And then, if you plot points, the